One, two. Oh. So I have to talk like that the whole time. Okay. Well, I'm not going to keep the gloves on, okay, because they're really sweaty and on. Oh, there we go. Alright folks, so my name's Dave, and I work for the Raspberry Pi Foundation, and I have a little presentation for you today about Astro Pi, which is the project that I'm working on.
If anyone is probably thinking, yes, he does wear that every day.
Okay. Right, I'm just waiting for my presentation to load. Hopefully. Hooray! Okay. So, Astro Pi is a collaborative project between the Raspberry Pi Foundation, the UK Space Agency, and the European Space Agency, and obviously this man, Tim Peake. Is there anybody in this room who doesn't know who that is? Okay, good. So I have been in schools before doing this kind of work where like half the kids put their hands up and I've had to lambast them for it. So thank goodness for that. So okay, so that's Tim Peake. The idea behind this project came about from an industry innovation and growth strategy review, which tasked the UK space companies, all the companies in the UK that contribute to spaceflight, with making some kind of school-based competition to engage schools with science and with technology and spaceflight, and to exploit the outreach possibilities offered by Tim's flight to the ISS as much as possible. So there's Tim. What we did is we've made an actual add-on board especially for the mission, which is called the Sense Hat, which you may have heard of. And there's Tim actually checking out the prototype of it. So in the hands closest to the camera, with a little spike sticking out, that's the prototype for it. And in the other hand is the actual production version, which is the one you can all go and get if you want to get it. So the Sense Hat. You've all seen this before. That's it at the top there, and there's a normal Raspberry Pi below it. Okay. Basically, all you do is you dock it onto the top of the Raspberry Pi, and then you have what we call the domestic Astro Pi, which is the Raspberry Pi that doesn't have the special flight case like that one down there. Okay, and if you've the main thing about this is that you can write code using that setup, and that code can be flown in space and run on an identical computer, which is what's inside the flight case. So, what's on the Sense Hat then? Is anybody here unfamiliar with this board? Have you all seen this before? Okay, so what I'll do is I'll just quickly go through what's on it. So if you look at the top there, you can see on the side it says humidity, and just below that you've got pressure. That's a pressure sensor and a humidity sensor, both of which can give you temperature as well. And then just to the left of that, it says Excel Gyro Mag. That's an accelerometer, a gyroscope, and a magnetometer all in one little chip. And that gives you all kinds of measurement of movement. And it can pick up how the space station is moving through space, how the Earth's magnetic field is changing, the direction of geomagnetic north, when they fire the reboost thrusters to maintain the station's orbital height, all kinds of cool stuff like that. And then that little silver thing in the bottom here, this thing, is a joystick. So if you wanted to program some games or something, you can program games with Tim Peake to play. Okay? And some people have done things like Snake and Tetris on there. Now, the main thing that you'll notice about the Sense Hat is this big matrix of LEDs. Okay, so you've got 8x8 LEDs. Okay, and you can program those to display any kind of icon or shape that you want. But you are working in very low resolution. You've got 8x8 pixels to work with. So those LEDs behave exactly like pixels. They've got a red element, a green element, and a blue element, just like a pixel on a TV or your phone. And you can program that they're multicolored, so you can get all kinds of like high fidelity things. And if you watch the one that's down there on the front, you'll see that it's changing colour, and every now and then the centre 4 pixels light up and show a different colour. Okay, so if you want to get something into space, you need something called a flight safety certificate. Okay, and these things are not trivial to get hold of. Okay, so step one was to make these flight cases. Now you can't just send a bare circuit board into space, because there's lots of sharp edges, there's all kinds of hazards that could be associated with it. So to defeat that, you create this very, very sleek, polished case, which will contain all the hardware that you want to fly, and that's usually the first thing you have to do. Now it's also got this huge heat sink on the bottom. Now, for most people who know about Raspberry Pi, that seems excessive, because Raspberry Pis don't produce a lot of heat, but in space, there's no convection. So what happens is, think of a hot CPU, the hot air is rising because cold air is coming down and displacing it by gravity. But in space, that hot air just stays there, baking and baking and baking, and gets hot. So you have to get rid of all your heat through thermal conduction, which is what those pins do. Each one of those pins can get rid of about 0.1 of a watt of heat. Okay, so we could actually put a Pi 2 or a Pi 3 in this thing and fly it, because it has that much heat dissipation capacity. Okay. Oh, and just one other thing, you can see the camera module, that's the flex of the camera module going up, and you can see the little light on the camera, that's in the base. So that's what it looks like when it's mounted on one of the ISS bogan arms. Now I haven't got one of those with us today, but if I just hold the flight unit up, you can see this stainless steel part on the side. That is the attachment for the bogan arm, and what it does is it holds it like that, and then they'll position it wherever they want it on the space station. You know, if they want to aim the camera out of the window, they'll just do that and then point that right against the window. Okay. Right. So what's actually inside the case? So you've got the sensor, which you've all seen, and then you have these two cameras. And there's two Astro Pis up on the space station. Okay, one has an infrared camera, one has the visible spectrum camera, which is the green one, and then you have this board, which you won't have seen before, and this isn't available to anyone. Okay, now that is just a real-time clock, a backup battery, and a pin out for the buttons. Okay, so that little row of pins there is where the actual push buttons on the flight unit connect. Now, if you look closely at the cameras, you can see that there's this weird goopy stuff on it. Now that stuff is called conformal coating, and it's a requirement for any circuitry that goes into space that it is coated in this special kind of like nail varnish like goopy stuff. Now what happens is any exposed tin, which is often used in solder, for example, in space, and it's something to do with zero gravity and temperature cycling, it causes this thing called tin whiskers, which is a weird metallurgical phenomenon where you get all these tiny little hairs of metal growing out of anything that's made of tin. Okay, and what happens is these things snap off, they go cartwheeling off in zero G, get caught in somewhere, and something goes wrong. And this actually caused the space shuttle computers to reboot once during a descent. So it can be quite a serious situation. So what happens is any circuitry that has any tin on it anywhere, which is all of the solder joints that you see on our boards, has to be coated in this stuff. And what happens is it doesn't stop the tin whiskers, they still grow, but it stops them breaking free. And it arrests them, it holds them in place. And also if another tin whisker is invading, it stops it from being able to short circuit anything. So we also had to do loads of different testing, and we had to present all of our test results to the European Space Agency to prove that we were allowed to go on the space station. So the first one we had to do was vibration. This is actually a massive vibration table that's designed to take satellites and all kinds of other payloads. But what we've done is we've just put our tiny little computer on there, and they set it up on the computer to vibrate in exactly the same way that the actual rocket would vibrate. And what it does, it sits there and it just goes, vibrates for England, and then you actually take your payload off and you examine it to see if anything's come loose, anything's snapped or anything like that. And you just check to see that your payload will survive the vibration situation of launch. Then we had to do a EMC testing, which might seem a bit strange to a lot of people, but what this is electromagnetic radiation. Does our payload give off any kind of weird radiation that's going to cause other systems problems on the ISS? So I don't know if you remember in the 80s when someone was vacuuming, the TV would go all mad. And that's because the vacuum cleaner was giving out loads of electromagnetic radiation which was interfering with TV. So for example, when they turn on the Astro Pi, does all the Wi-Fi drop on the ISS? You know, that's the kind of thing that's to test for. Okay, so this one's probably my favourite test, this one here. Now this one's called off-gassing. And what happens is, this is a bell jar, they put the payload in there, along with some SD cards, basically the entire payload that's going to go. They pump all the air out, so it's a vacuum, and then they pump in this weird synthetic air, heat the whole thing up to about 50 degrees Celsius, and then they leave it there for about 72 hours. And then after that, they pump all the air back out, and any air that's changed in there must have been released by the payload. Okay? So that's the test to see if we're gassing the astronauts. Okay? The one up in the top corner, that's the thermal radiation test, which is the proof that the heatsink works. So those little things that are stuck on all the sides, they're small temperature sensors, and we had to put it inside a small box, put it up to CPU 100%, GPU 100%, stress it to maximum performance, and then measure the temperature to see if it ever got up to 45 degrees Celsius or not. And that's the maximum hard limit. If any surface of your payload gets above that temperature, you fail and you're not allowed to go. Okay? And then the most unscientific one of all is this one here. This is the sharp edges inspection. And all they do, they have these special gloves, and they just pick it up, and they just go like that, and just feel it. And if it snags anywhere, you fail. So I was stood right next to this guy doing this test, just holding my breath, just hoping this was going to work, and thankfully it did, and we didn't have to do anything else. And then the last test is the actual a simulation of what will happen on orbit, and that photo is taken in the Columbus mock-up module in Germany. So we also ran a competition, which some of you may have entered. So the competition we ran was to farm the community for code to be run in space. Okay, so it was divided into two stages, primary and secondary. So the primary school kids only had to submit an idea about how they wanted to use the payload. So the idea would be that they would think, I want to use the Astro Pi to, say, detect the presence of the crew using humidity, and then Raspberry Pi worked with the schools that won that to write the code and prepare it for spaceflight. But the secondary school kids, we expected a bit more from them. We actually expected them to go away, use their own SenseHat and Raspberry Pi to write some actual code themselves, which would then be flown in space. So that's what we found, is that single thing is the single most profound motivating factor for participation in this thing. The fact that your code will run in space, something that you have made, can be up there in space doing something. Okay, that is the amazing thing about Astro Pi. So I just want to quickly go through some of the people that won this. Oops, that's all right. There we go. So this is Cranmere Clove Club, and I don't know if any of you were here yesterday. They were here presenting the results of their experiment yesterday. Okay, now what their one does is called Crew Detector. Originally it was called Sweaty Astronaut. We had to change the name because ESA don't have a sense of humour. So what basically all it does, I can run it on here for you now. I'll just start it up on this one. So what it does is it looks at the humidity sensor in the loop. So it's constantly going, what's the humidity, what's the humidity, and if it detects an increase in humidity, it will then try and take a photo on the camera. So the idea is that they set it up in the Columbus module, and then any time it tries to, it detects humidity, it detects a picture, and it's sensitive enough to detect when there's an astronaut working nearby. Okay? And they had 11 really good pictures come back from the ISS just recently, one of which was just Tim posing for it, and the others are all him just working, doing stuff. So that's actually like these kids have written code, it's run in space, and they've got the pictures back, which is the product of their code. So this is Hannah Belshaw. She wrote a Minecraft program which takes data from all the sensors on the Astro Pi, logs it into a data file, and then she gets that data file back. It's just a normal flat CSV file, and then they load it up in Minecraft and display the data visually in Minecraft. So what actually happens is you have these blocks which are moving up and down to show you what the temperature and the humidity is doing, and the pressure. And then they have this big blocky ISS made out of lots of blocks that moves and tilts and stuff in the sky. And that's a really cool one. You can go online and download this code and just run it if you want to. So these guys are from Yorkshire. They wrote a program called Flags. And what it does is it calculates where the ISS will be, predictively. So it's doing it offline, because the Astro Pi cannot be connected to the LAN up there. It's not online, it's offline. So they actually calculate using orbital mechanics from the known telemetry of where the ISS has been and where it's going, where it should be given a particular time. And that gives them a latitude and longitude. And then they work out what country that is within, and then they show the flag on the LED matrix. So it's quite good actually. That one's actually almost like a heads-up display for the astronauts. So it's less scientific but more kind of useful. So I'll just run that one as well. Now, if this one shows a twinkly blue-green pattern, it means it's above the sea. So you might see that it's above the sea right now. So this is Oliver Turnbull. His one is a infrared spectrum environmental monitoring program. And what it does is it takes pictures through the hatch window of the Earth, and then it analyses them for something called natural vegetation differential index, which is a kind of false colour processing. So plants reflect different levels of infrared light based on how healthy they are, based on how much chlorophyll is going on in the plant. So you can actually see from a whole continent, from one of his pictures, where the plants are that are most healthy and where they are least healthy. So you can actually see that there's like an urban whole in this kind of like false coloured image. It's really clever. And these guys wrote a whole series of games, one of which was Snake. And their actual experiment is an experiment on Tim to see what his reaction time is like. So does his reaction time get quicker or slower throughout the mission? And these guys just completely blew us away. These were A-level students, and what they've done is they've repurposed the Raspberry Pi camera module as a radiation detector. And this kind of really impressive. So what you do, Tim has actually had to get one of the Astro Pis and blank off the camera sensor. So he gets a bit of grey tape and just sticks it over the camera sensor lens. And that stops any light getting into the lens, right? Don't worry. So it stops any light getting into the lens, but high energy radiation can penetrate the bit of tape, right? And what you get is this kind of effect. So if there's space radiation going on, it'll still get through, and it fools the sensor into thinking it's detecting light. And you get these little specks and these little traces of where there's radiation happening. And not only did they do that, they wrote code to count the specks. So it produces a measurement of the level of radiation that's happening. So they're going to run that in different modules of the ISS to see where the radiation and where the shielding is better in the ISS and stuff. So after that, we actually had to go and train Tim on the payload. So there's me with Tim in Germany in the European mock-up module, and we're about to take a photo of him posing with it. And there he is. And this is Ozzy, who is one of the ones who wrote the crew detector program, and he's holding one of the 3D printed versions of the flight case to completely mock it up again. So I've got one of the 3D printed versions of the flight case here. If anyone wants to come and have a look at it, it's in 4 pieces. I'll leave it down there at the end. You can have a look at it. If your school's got a 3D printer, you can just go and mock up and make your own version of the flight case. And that's kind of what they come out like. That one's actually quite a nice one that's been made out of a liquid polymer 3D printer. But we've got this resource. You can just go online and find it on our website, and it'll show you all the steps you need to follow, all the bits you need to get to build your own Astro Pi. Okay? And that's one of the really great ways to engage kids with this, is to get them to make something. Okay? So how do we get to the ISS? We got to the ISS on this spacecraft. And this is a Cygnus cargo vehicle. So for the most of the time, we were going to be actually on the Soyuz vehicle with Tim. Okay? But we got bumped off the Soyuz due to a cargo overbooking, and we put onto this vehicle, which is just a massive cargo freighter. It's unmanned, no one goes on it. Okay? And just to show you, that's the Cygnus. If you look in the top left-hand corner, that's the Cygnus spacecraft, and that's one of the bags that's got our payload in it. And if you look closely in there, you see Astro Pi hardware. So I'm not lying, it is actually up there. Okay? So now this is where I want to do some sound. So where's my sound engineer guy?
Let's see what happens.
Yeah? Let's see if it works.
Sell the mic next to the...
Down here?
Yeah.
Mine may not work.
T-minus 48 seconds and counting.
Got it.
Atlas tank signal in step 3. T-minus 30 seconds and counting. 25. Go now. Go start. Go coding 4. 20. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off. On the shoulders of Atlas, the SS Deep Slate II orbital ATK Cygnus spacecraft soars toward the International Space Station. The unit's going close to control.
There it is approaching the ISS. And then on the 9th of December, there it is docked with the ISS. You can see they grapple it with the ice with the arm and they pull it in, dock it. And then on the 15th of December, we all know what happened on the 15th.
Vehicle to internal power. So at T minus 35 seconds, the first umbilical tower has separated from the booster. That second tower will go at about 15 seconds away from launch. We're at 24 and counting now. Ground umbilical to the third stage has been disconnected. Second umbilical tower now separated. Boosters igniting, the engines firing. Ramping up the flight speed. And liftoff. Liftoff of Tim Coper, Yuri Malechenko, and Timothy Peake on their way to the International Space Station.
Hey. So there you go, there's Tim in the European Columbus module. That was the 15th of December, and then everything went quiet, and on the 4th of January, we got this picture back. And there it is, that is actually the Astro PI in the Columbus module. Okay. Now on the 2nd of February, this is actually not turned on yet. So it was left until the 2nd of February before it powered up. And then we introduced this video, which I'm not going to play now because it's about 2 or 3 minutes long, where we introduced Ed and Izzy, the anthropomorphized versions of the 2 Astro PIs up there. And there's a really nice video online, which is an animated cartoon showing how these 2 characters got up to the space station, which I thoroughly recommend you go and watch after coming out here. And then on the 16th of February, that's Izzy being turned on, actually set up looking out of a hatch window. And this is actually my favourite picture that's come back from the ISS yet, and it's actually showing the whole of the hatch. So behind that door is space, which is pretty cool. Okay? And actually it looks directly down onto the Earth. So this is the one that's taking the infrared pictures of the Earth, which is analysing for it. Now, can everyone just put their phones away for a second, because I've got like a little bit of a sneaky thing to show you, and it's not going to violate any of our things, so don't worry. This is going to be up on the screen for a few seconds, so can you put your camera away? Okay, okay, right. So, it's not Tim in his underwear, don't worry. There you go. It's Tim talking about Astro PI. That's all good. So look out for that. The BBC will be showing that video. We've offered it to them as a news exclusive. So Tim is actually talking about the Astro PI on the space station. Okay. Now, I want to talk about the coding challenges now. It's still not too late to get your code up into space. So, okay, yeah. So we have 2 coding challenges which are open until 31st of March, where the prize is to have your code flown in space and run by Tim Peake. There's 2 challenges you can enter. One is to actually repurpose the Astro PI to make it into an MP3 player. Okay? So basically what you're going to do is your code is going to be showing an iPod-like interface on here, and then you have like play, stop, rewind, back, next track, that kind of thing. Or you can actually program some music using Sonic Pi, which is another kind of programming tool, which is available on the Raspberry Pi for free. So you can choose to enter both of those or just one of them. It's entirely up to you. Okay? So just think about that. Your code could be in space running, and Tim could be listening to music that you've composed. Okay? So that's the basic hook about this. That's the URL. Go to this URL if you want to enter the challenges. Please take your phones out and take a picture of that. Okay? So, That's basically, so, and the deadline is the 31st of March, okay, so you have to get your code in by then, okay? So all you need to know is on that website. Just go to that URL and everything you need to know is on there, okay? Anyone else taking pictures? Can we go on to the next one? Okay. Right, so if you want to follow the mission, that's our Facebook and Twitter accounts. So Ed and Izzy, the two anthropomorphized Astro PIs, they have their own Twitter account. And if you ask them questions, they answer them. Okay? Amazingly. Okay, now, this next slide is also a bit of a world exclusive. Okay? We're currently in talks with ESA. This is not confirmed at all yet, but we are in talks with ESA to use this man. This is Thomas Pasquet, French astronaut. We've got any French nationals here? Okay, so we're talking to ESA at the moment about using. He's flying to the ISS in November this year for 6 months, and they're interested in using Astro PI as part of his educational outreach as well. Okay, he's one of Tim's classmates, and he's the only one of the 6 of that class that hasn't flown yet. So he's going to be the last one to go up, and he's going to be doing Astro PI 2.0, hopefully, depending if we can get ESA to do everything where we want them to. So, ask me anything. Any questions? Yes?
The 2 competitions you mentioned, are they the schools or can individuals enter?
Individuals can enter it, yes. Individuals can enter it, code clubs can enter it, youth centres can enter it, anyone can enter it, homeschoolers can enter it, anything. Yeah. Okay.
Is there an operation?
Sorry?
Is an operation?
18. So there's 4 age groups. It's 11 under, 11 to 14, 14 to 16, and 16 to 18. Okay.
Yeah, after you send new code up, is it they put it on the SD cards or something because the actual files are offline?
Yeah, so that's how the code is transferred. So what happens is Tim will take one of the SD cards, put it in a crew support laptop. He'll receive the files through the space-to-ground radio system, transfer them onto the boot partition of the Raspberry Pi SD card, and then the code actually is, when it boots up, it automatically pulls anything and it finds on the boot partition. So that's how it works. Yeah.
When you were testing etc. before, did everything go wrong?
Yeah, actually, a couple of things did go wrong. The first thing that went wrong is when we got these cases back from the manufacturers, all of these pins had really sharp edges, and it was like there was no way that was going to pass the sharp edges inspection. So we had to send it back and get them to modify the model slightly to sort of radius these edges a little bit, because you could have actually just like gone and cut yourself. So yeah. That was probably the main thing that went wrong. There was no kind of non-compliance in the ENC or any of the other tests that we did. So, yeah.
Where did you get your spacesuit from?
This is on loan from the UK Space Agency. Yeah, it's actually a costume one. It's not a real one. It doesn't hold. It's not airtight. Okay. Any other questions? No, it doesn't have a cooling pack, which is why I don't close it. Because if you close it, you can't breathe. So any other questions about it? If anyone wants to come down and have a look at the 3D printed one, please do, because I totally encourage you to go out and 3D print your own, because once you've got your own Astro Pi, when you're prototyping and testing your software for Tim, you can work out all like the ergonomics of using your software. So if it's like uncomfortable to press down at the same time as you're pressing up or something like that, you can work that out by actually physically owning one of these yourself. Okay? So if your school's got a 3D printer, each part it's in 4 pieces, and each part takes it's probably about 4 or 5 hours each to print, because they're quite complicated models. So, any other questions? Yeah. The sense hat, yes. Yeah. Oh, the real-time clock hat. You don't need that. You don't need that to do this. So if I just open it up, that's what it looks like inside. There you go. So it's just a Raspberry Pi with a hat on top of it. Okay. So yeah, and those are the 4 pieces. I'll just line them up. One at a time.